same one for the spring.
If I used the same exam from the spring, I'd be really disappointed if anybody failed it.
Yeah, see, that would be a great test to see if we practiced in all the capacity that
Do you know what's a better way to test if you practiced? To give you new problems that see how well you understand it.
Or that's not practice, understand. You practice a lot and understand.
That's true.
But then you gave 100% of that practice, you still don't understand.
You want me to give 100% just for you practicing?
100% participation.
Ah.
I like
I participated in the
points.
exam.
I
need just 90 points.
You know what? I had a professor in one of my senior year classes who had on her exam as the last question, like, what is Dr. Cole's favorite instrument? You know? And that was worth points. You had to choose the correct one. But it was something she talked about over and over and over in our instrumentation course. So it was funny, but it was like weird. Like I'm actually being graded on this question that is not relevant to the class content. And then other professors that are like 2 points for writing below what you learned this semester, or what you liked, or what you didn't like. It's like, you know what? You can fill out your course evals. I don't know. As much as I love a humorous class environment, I have just never felt drawn to putting humorous questions on my exams. And I feel like some students expect it, like they want to come into the final and get like one little giggle out of my class. And I just make them cry instead, you know?
Usually when I get questions like that, it's like a bonus question where like if you write what you enjoyed about the class or like a critique, you give us a bonus point.
Sure. And I do bonus points too, but
no, I'm not saying I expect it. I'm just saying it's not normally like part of like you have to answer it. You can answer if you want to.
Yeah, sure. And I accept that as better than like being worth points. Mm-hmm. But if my bonus questions were not just testing more of your understanding, I wouldn't have bonus questions. I don't think an exam should need bonus questions. I think if an exam is done well and if the class is taught well, you should not need bonus points. You should not need extra credit. The only reason that I give extra credit is if you show me your understanding more. That's it. I don't give extra credit for extracurricular activities. I don't give extra credit for giving me silly little responses that you can put on your course eval. All right, let's talk about class content. PKAs. We had 2 reasons so far. We said PKA decreases, meaning it gets more acidic. Although the first time I put this on here, I said PKA increases, it gets less acidic. PKA increases or decreases with decreasing induction. And to be fair, we have to be a little bit flexible with how we understand induction. Esters have an electronegative atom, the ester linkage oxygen, that pulls electron density away from the carbonyl carbon, pulls electron density away from the alpha carbon. But at the same time, that ester is donating electrons to the carbonyl through resonance. And so that kind of negates the induction it has from its electron pull and actually increases induction in the opposite direction. And then we have ketones. You know, they have just carbon groups that pushes more electron density. And then we have aldehydes. Just that hydrogen doesn't do much. Then we saw that pKa decreases with increasing substitution. And we actually reasoned that the enolate that forms is a more substituted alkene. More substituted alkene is more stable, which means it should be easier to form. More acidic alpha carbon. And lastly, we're going to find that pKa decreases with increasing resonance in the conjugate base, increasing resonance in the enolate. So I gave you guys some pKa values yesterday. I never expect you to memorize pKa values. I actively discourage it, actually. I don't know that memorizing pKa's is the most useful thing to do. Maybe recognizing general trends, but definitely being able to rank across a broad spectrum is important. But specific pKa's, not the ideal. Caesar?
So the pKa increasing resonance.
In the conjugate base, in the enolate, increasing resonance.
In the conjugate base.
We're going to look at our examples here in a second. So we did look at aldehydes, ketones, and esters. We said aldehydes, their pKa ranges from maybe 15 to 17. Ketones range more like 20. Esters range higher towards 25. So there's a pretty big discrepancy between how acidic the alpha carbon of a aldehyde is and how acidic the alpha carbon of an ester is. But nonetheless, still acidic. And then we only observed the pKa with increasing substitutions in the context of aldehydes. But we should be able to make the same assertion. If a primary ester alpha carbon had a pKa around 25, then maybe a secondary alpha carbon on an ester is around 24, and maybe a tertiary is around 23, probably in those 1 to 2 orders of magnitude. Same with the ketone, from 20 maybe down to 19 and 18. But again, it all depends on the specific molecule too. If we went and looked at a secondary ketone that had a benzene group next to it versus a secondary ketone that didn't, pKa's there are probably going to differ quite a bit as well. So now with resonance, what I actually want to look at are 2 very common reagents. The first of them is acetoacidic ester. I'm going to name this one because this is a reagent we're going to use more in this section. You guys know I've talked to you quite a bit about that ACET prefix and how it means a 2-carbon carbonyl, acetonitrile, acetaldehyde, acetic acid, acetate, the 2-carbon ester. So this is an acetate ester, but that's just counting these 2 carbons and the ester. But this alpha carbon of the ester is actually substituted by another 2-carbon carbonyl group. So this is referred to as acetoacetic. It's a 2-carbon carbonyl group that is substituted by a 2-carbon carbonyl group. If that's not one of the dumbest names I've ever heard, I don't know. I don't know what to tell you. I would have called it here's your ester carbon, alpha beta. That's a beta keto ester. That's a functional group that we saw introduced for the first time yesterday. So I would have called this 3-oxobutanoate. That's the ester. Whatever the alkyl group is, 3-oxobutanoate. But it's referred to as acetoacetic ester. Okay, I digress. Let's look at a couple of positions here. We've already seen the pKa value for an alpha hydrogen like this. Can you predict the rough pKa value for that alpha hydrogen? About 20? Because it resembles what? It resembles a ketone. But that's not the only alpha hydrogen in this compound, is it? There's also these alpha hydrogens here. When these are deprotonated, that alpha carbon takes on a lone pair between two carbonyls. So we've already seen that enolates are constantly in resonance. Enolates place the negative charge on the O and on the carbon. But now I'm able to actually see resonance between both of the carbonyls. I apologize for kind of the awkward orientation of this. So I can go from one resonance form where the oxygen on the right holds the negative charge, and I can look at the other resonance form where the oxygen on the left holds the negative charge. 3 total resonance forms. To clarify, how many resonance forms did our other enolates have? Two resonance forms. The resonance form where the alpha carbon holds the negative charge and where the oxygen holds the negative charge. Now we have 3 resonance forms. Alpha carbon, oxygen 1, oxygen 2. I want you to think about how you might describe that alpha carbon. Is it alpha to a ketone, alpha to an ester, alpha to an aldehyde? Some combination of those? The green alpha hydrogen. How would you describe it? Yeah, it's alpha to both a ketone and an ester. Good. So where do you think its pKa would fall?
I think it's going to be quite a bit less because usually resonance is a pretty strong thing, especially since it's between 2 oxygens, which I feel like is going to make the conjugate base really stable, so it's going to make it a bit more acidic.
Okay, so increasing resonance is usually a big effect. Compare phenol to methanol, where methanol has a pKa around 15, phenol is 10,000 times more acidic, even though it places a negative charge on carbon atoms in the aromatic ring. Phenol has that increased resonance. But then compare phenol to acetic acid. Phenol places the negative charge on 3 carbon atoms through resonance. So that's 4 total resonance forms. But acetic acid only has 2 resonance forms. In both of them, the negative charge is placed on an oxygen. And acetic acid is 10,000 times more acidic. 100,000 times more acidic than phenol. Less resonance, but with more appropriate charge placement in those resonance forms. So resonance is big. Charge placement is also big. And what we get here is increased resonance. We can say that these 2 forms, that's pretty similar to what all of our enolates give us. But we get 1 increased resonance form, and it places it on an electronegative atom. So where do you think the pKa here is going to fall? Compared to esters at pKa of 25, higher or lower? Lower. Compared to ketones, pKa of 20, higher or lower? Compared to aldehydes, pKa of, let's say even the most substituted aldehyde, tertiary aldehyde, alpha carbon, 15, higher or lower? Lower. Okay, compared to phenol, keep in mind that phenol is an OH, which is generally more acidic than CH. How do you think phenol with a pKa of 10 compares to this CH bond? Higher or lower? Or equivalent?
It might be slightly lower. I might be like overestimating here, but
Maybe more acidic than phenol.
maybe I don't know. To me, you said like it has the extra. Oh, I don't know. You said it was like 10,000 in like this other case, so I don't know.
Okay,
I
so
think it might be slightly lower.
so this has a pKa of 10, and the negative charge moves from oxygen to 3 of the carbon atoms, but acetic acid has a pKa of 5. That's only 2 resonance forms, but they're both on oxygen.
So I think it's less than 10.
More acidic than 10.
Yeah, I don't know, but the way you're looking at it makes me
I'm-
question myself. but
This
yes.
is just like, this is you developing your chemical intuition. This is you struggling to understand how many resonance forms does it take? Where is that charge placed? What is that going to do?
I'll say it's less.
So there's a couple of differences. One, when this gets deprotonated, it is the OH bond that's being deprotonated versus a CH bond. And generally CH, compared to OH, much, much, much less acidic. Much, much higher pKa. But this has 3 resonance forms. 2 out of the 3 place it on an oxygen. This has 4 resonance forms. 3 out of 4 place it on a carbon. So there's kind of this balance between the bond that's being deprotonated and where that charge is being held. And the answer is 11.
That's close.
It's really close. And I actually want that to sound really strange to you guys. This CH bond is nearly as acidic as phenol. This CH bond is 10,000 times more acidic than water. Ruminate on that. Okay, there is another compound that I want us to be familiar with. This is referred to as a malonic ester. And once again, we're going to be looking at the alpha hydrogens here between it. When one of those alpha hydrogens is deprotonated, the malonic ester takes on that negative charge at the alpha carbon, and then of course that negative charge is delocalized. And that negative charge can be seen moving between both of the oxygens. I want you to be thinking about what you would predict the pKa to be here. What is the closest compound to compare this one to? The aldehyde, the ketone, the ester, or the acetoacetic ester? Yeah. Acetoacetic. I don't know how to pronounce it, to be quite honest. I always say acetoacidic, but it's not acidic. It's
Acetic?
well, it's
Acetic acid?
it's I think it should be pronounced the same way as acetic acid. So acetoacetic. I think it's that repeating of the aceta that sounds really weird. Acetoacidic. How about we call it a beta keto ester? So the most comparable thing is acetoacidic ester. Do you think this would be more acidic or less acidic?
Less.
Tell me why.
There's more induction.
Yeah, more ester groups, more induction from more resonance. So, and I know this is actually, that sounds weird when I say that. Not more resonance in the conjugate base, more induction from resonance of the ester group with the carbonyl. That's going to decrease acidity, increase pKa. Okay, so let's say when we had an alpha hydrogen that was next to a ketone, pKa around 20. Alpha hydrogen next to an ester, pKa around 25. 5 orders of magnitude for that inductive effect. I'm basically making the same swap here, aren't I? Other than now both of my conjugate bases, both of my enolates, have multiple resonance forms with more electronegative atoms. So how might you predict the pKa is going to change here?
17.
Up to 17?
217.
So this alpha hydrogen between two carbonyls might be on the same order of magnitude as the least substituted aldehyde. It's not even more acidic than the most substituted aldehyde. It's actually less acidic than the most substituted aldehyde. This is what we're fleshing out, right? 15 was kind of the most acidic range for our aldehydes. So if we go to 17, we're saying this is less acidic than an aldehyde's alpha hydrogen, even though it's got more resonance forms with more electronegative atoms.
I think slightly less than 17. Maybe like 15, 16-ish, I don't know.
So still like on par with how acidic the alpha hydrogen of an aldehyde would be?
I think it's like 13.
Why?
Less than an aldehyde.
So less than an aldehyde, you're really just shooting the gap.
Yeah.
Somewhere between 11 and 15, 13.
I mean, if above it had such an effect induction did with, like you said, the 5 orders of magnitude, I feel like it should be like similar to that, but maybe not exactly. I was thinking like 15, but
Okay, so 5 orders of magnitude between ester and ketone, but then also 3 orders of magnitude between ketone and aldehyde.
yeah. But this is adding on another ester group, right?
And another resonance,
Yeah.
and then another negatively charged oxygen.
This is not a lot higher than the ester if it has more induction and also like resonance. It should, I think it should be higher than.
Higher than an ester originally?
Yeah.
Well, this has more resonance forms in the conjugate base than just a normal ester.
Right, so
That's going to bring the pKa down
because of resonance.
because of increased
Might
resonance,
be a good guess.
plus because of the negative charge being on 2 oxygens, not just 1.
Right, but
So induction will play a role compared to this guy, but in that the amount of induction isn't going to make it less acidic than a normal ester.
the resonance would bring it more down than what the induction is.
That's right. Okay, here's our pKa. Sam, did you Google it?
No, not at all.
Yeah, 15 is what we're looking at. It does shoot the gap between our most acidic aldehyde alpha hydrogen and our acetoacidic ester. Okay,
Are we going to have to do that in the exam?
you're going to have to rank alpha hydrogens for sure.
We won't have to guess if it's 20 or
Nope,
22, whatever.
nope. But you will have to gauge these conditions. Is it adjacent to an aldehyde? Is it adjacent to an ester? Is it between two carbonyls? And you know there's a lot of other situations we could envision. We have this beta keto ester and a beta ester ester. But we don't have a beta keto ketone, we don't have a beta keto aldehyde, we don't have a beta aldehyde ester, we don't have a beta aldehyde ketone. So there's a lot of other conditions. These are just the most common ones for us to see. Okay? All right. Now, staying in this vein of acidity, we want to talk about regiochemistry. So we're going to look at kinetic and thermodynamic bases. This is really most relevant with ketones, but we're going to introduce a reagent here that is very useful for all different kinds of reactions. I'm going to give us this energy diagram. This is energy along the y-axis and a two-way reaction coordinate along the bottom. That means I'm going to put a starting material in the middle. I'm going to show two different things that it can form in either direction and the energy barriers to make them. Can you name that compound? Good. I would accept 3-methylbutanone because there is no 3-methyl-1-butanone. There is no 3-methyl-3-butanone. But I think a lot of places you would see it named 3-methyl-2-butanone. To be fair, 2-butanone is super repetitive because there cannot be a 3-butanone, that's just numbering the wrong way, and there cannot be a 1-butanone because that's an aldehyde. So butanone would be a totally acceptable name. You don't need the locant in that compound. 3-methyl-butanone or 3-methyl-2-butanone. How many alpha hydrogens does it have? Be careful, I'm asking how many alpha hydrogens, not how many alpha positions. 4 alpha hydrogens. 3 of them are on this less substituted side. 1 of them is on a more substituted side. Which of them is more acidic? The more substituted side is more acidic. But which one requires more energy to remove?
One that's less acidic.
Okay, this is an interesting question. If it's less acidic, it should be harder to take away. Is that necessarily true? Because remember, the measure of an acid is simply how bad its conjugate base is. So maybe it is a little bit harder to remove a more acidic hydrogen, but the conjugate base doesn't react as much. So it's a better acid even if it's harder to form.
Could the H on the right, the one that has a 3, be easier just because it's less, what's the word?
Caesar?
Too much space.
Sterics.
Sterics, that's the word. Less sterically hindered.
Exactly that. So if we form an enolate with the alpha hydrogen on the right, it doesn't take much energy, but you don't get much stabilization from it either, because it's the least substituted enol that can form, or enolate in this case. Now compare that to the more substituted carbon on the right, This carbon does require more energy. It's more sterically strained. So having a base go in to that tertiary carbon and remove a hydrogen requires a lot of steric strain is overcome. But the end result is that you get a more stable conjugate base. So we refer to these conjugate bases as the thermodynamic and the kinetic product. You guys might have learned this in OChem 1. You might have learned these terms also in Gen Chem. Do you have any intuition about which of these is a thermodynamic product and which of these is a kinetic product? Can you talk to me about your logic there? You said the one that forms faster is the kinetic product.
Yeah.
How did you make that connection? How do you remember that?
Teacher said.
What teacher? Your Gen Chem 2 teacher?
Ron.
In OChem 1, the one that forms faster is the kinetic product. Kinetic makes you think of speed, movement. So speed, quickest to form is the kinetic product. That's exactly it. That's a good way of thinking about it too. So least amount of energy, but the least stable, this is our kinetic product. Just because it forms the easiest doesn't mean it's the most acidic. You can form that base, but notice that that base is higher in energy than this base. So it's also the most likely to react as a base and go backwards. What about thermodynamic? If you can remember kinetic forms fastest, look for the lowest energy hump. That works, and now you can just process of elimination, figure out thermodynamic. But what is there a way to remember what the thermodynamic product is by looking at this? That's true, but does that kind of connect to the term thermodynamic at all?
No.
I feel like if you were to add like heat to this, you'd more likely make that product because it's able to do the more energy and then it releases more heat because it goes down and releases that.
So you're thinking like thermo heat.
Yeah.
Add heat to get over the big barrier. That gives you the thermodynamic. The way that I remember it is thermodynamic is the most dynamic. It requires the most energy, the highest high, but it gives off the most energy, the lowest low. So you've got the most dynamic energy profile for the thermodynamic product. Now I titled this not as thermodynamic products and kinetic products, but as thermodynamic bases and kinetic bases. A thermodynamic base is something that we'll refer to as something that easily overcomes that energy barrier. Something that easily overcomes steric strain. Like a thermodynamic base is the one that forms the thermodynamic product. So a thermodynamic base isn't hindered by this steric strain. To a thermodynamic base, this energy gap between our activation barriers is small.
So
Just goes one way or the other.
that's a thermodynamic base, or that's
There's no base here. No.
Oh,
That's.
so the thermodynamic base.
I'm going to give a list of our bases. Yep,
You get the thermodynamic.
that's right. That's okay. So, a thermodynamic base is what we'll use to generate the thermodynamic product. That's going to be something that doesn't experience much steric strain. So we're looking at hydroxide or alkoxides. things that are small like methoxide, ethoxide. People have different arguments to make when the carbon chain gets larger than that, like propoxide or isopropoxide. But these are the most common thermodynamic bases that we will use. Sam, you got a question about that?
No, I was just trying to decide what was after the RO minus. Is that equal something?
Yeah, so like, for example, alkoxide
Oh.
could be methoxide, ethoxide, etc. All right, well, here's a limitation about reacting our carbonyls with these thermodynamic bases. The equilibrium doesn't really favor production of the enolate. We said that this alpha hydrogen has a pKa maybe around 17 for this ketone, and water has a pKa around 16. So the equilibrium does not favor production of the enolate. And there is a downfall about that. Equilibrium doesn't favor enolate, which means both enolate and carbonyl exist at the same time. We're not going to cover it just yet, but we're going to come back to this. And see how this leads to the aldol and Claisen reactions. You guys might remember, for those of you who are in lab, we had a synthesis of a Grignard. We had solid magnesium, and we added bromobenzene. So as soon as the bromobenzene is added, it reacts with the magnesium and creates phenyl Grignard. But if phenyl Grignard is in the presence of bromobenzene, they will react together and cause a substitution reaction, which ruins each other. So if you're trying to make an enolate to do something with that enolate, but it also exists in the presence of an electrophile like the original carbonyl, then they can react together, and you can't control the enolate for what you wanted to do with it. I also want to give an example with an ester, because with an ester, I mentioned yesterday, it's very important that you have an ester that matches the base. So here I have an ethyl ester, OET, and I'm reacting it with eth oxide. That way, there's no chance for trans-esterification. And I make ethanol and my ester enolate. Ten orders of magnitude different between these two compounds, between the alpha carbon on the left and the alcohol on the right. The alcohol is 10 orders of magnitude more acidic, which means if ethoxide acts as the base, if the ester enolate forms and ethanol forms, it is much more likely that ethanol reacts with the enolate to reverse the reaction. That's 10 to the 10 times more acidic. 10 billion times more acidic. So we can say at equilibrium, we would have about 99 parts of ester to 1 part enolate. And once again, this issue is what leads to our aldol and our Claisen reactions. So having both your ketone, your carbonyl, and your enolate version of a carbonyl in reaction at the same time can lead to reactions between them. Our kinetic bases then, those are bases that are so bulky on their own that this difference in the activation energy actually causes them to only react with the less substituted side. They're inhibited from going to the more substituted side. So this would be something like tert butoxide. Few different ways that you can write it. Tert butoxide we used back in OChem 1 to do exactly this, to go to the less substituted side, to act as this kinetic base. And now there's a new one that we'll be introducing. So I don't want you guys to confuse this reagent with LaH, lithium aluminum hydride. This is LDA, lithium diisopropyl amide. And you can see how LDA is also a sterically hindered strong base. All right, so if we use tert butoxide, we still get this issue the equilibrium doesn't favor one side or the other. So as soon as we add tert butoxide, we will have a solution that has both the enolate and the carbonyl. That might be ideal if you're trying to run an aldol or a Claisen reaction. But if you don't want to run these types of reactions, this isn't actually great. But if we introduce LDA, LDA is such a strong base, and we'll look at the differences in pKa values. That whether you're working with a carbonyl, an aldehyde, or a ketone, or an ester, LDA will run 100% conversion The ketone, the aldehyde, pKa's ranging between 15 and 20. The ester pKa around 25. But the amine that forms has a pKa around 35. That pKa of the amine makes it a much, much worse base than any of our carbonyl starting materials. So at equilibrium, we would actually see this flip. Maybe 1 part carbonyl to 99 parts enolate. Also, I just want to demonstrate for you guys the mechanism for this. I want to kind of clarify what I'm putting there with LDAH plus. So LDA deprotonates an alpha hydrogen from the less substituted side. That CH bond moves in to form a CO double or a CC double bond, which breaks the CO double bond into the enolate. And that leaves me with lithium ion plus diisopropyl amine. So when I have on the board over there LDAH plus, it's not that the amine is positively charged. The plus is actually lithium. I can't say LDA without implying lithium. But lithium is no longer ionically bonded to the nitrogen. Lithium technically would be ionically bonded to the oxygen now. So it's this little cluster that I'm labeling here as LDAH plus. But I want you to recognize the plus charge is lithium, not the neutral amine. And the amine has a pKa around 35. Terrible, terrible acid. So once it acts as a base, it doesn't go back. And I know I'm saying here 1 to 99, but this is basically complete enolization. You do not get any remaining reagent here. All right, so I want to just go through a couple of examples with you guys. only because what I put up there was less than 1%, and LDA will make nearly 100%. This doesn't have the double bond in the correct spot.
Wasn't going to the less substituted person.
The less substituted alpha carbon. How many alpha carbons does an ester have? No, only one. So with an ester, it doesn't quite matter. Sorry, not a great base. Or what I should say is good type of base. No, same reason, not the right base.
That's gonna go on this side, that's the one I'm using.
Correct. Here we used ETO minus because this was only T. Now we have O and E
Oh, you wanna use the base that is
matches. Good, good. Good, good. It's kind of funny to drop that way. But you got it right. That looks great. Good work. The only thing that I would have added to that second one that most of you guys have gotten is that we're forming the enolate at 100%. Or, maybe I should say greater than 99% conversion.
You put it EP, but it's NE.
I did, thank you. Thanks for catching that. Changed my ester. Which is the whole point of this. I'm going to form an enolate, but I'm going to only form a small amount. So I'm going to use a thermodynamic base. That thermodynamic base could be hydroxide or any alkoxide. But because I'm working with an ester, the base has to match my ester linkage. So if you had put ETO minus, you would have lost points. If you had put hydroxide, you would have lost points. You would have gotten some points for making sure you chose a thermodynamic base that forms the enolate to a small amount. But you would have lost some points for not choosing the right base to match the ester linkage. And then down here, aldehyde or ketone, starting material. Yeah, secondary enolate, right? That O minus is connected to a secondary carbon. So that's going to be a secondary carbonyl. What's wrong with that problem? Oh, you guys didn't catch it. That's okay. That's why we're going over it now.
Would it have made the resubstituted alkene?
This is not the enolate that forms from this reaction. Did you see that? Here's my ketone. It has a more substituted alpha carbon and a less substituted. I'm introducing LDA, which is going to be governed by that steric strain, and it will go to the less substituted position, which means this is not the enolate that forms in the first place. The enolate that forms simply has the alkene on the other position. Forms the least substituted enolate. I hate to say it, I didn't do that intentionally, but I'm not mad about it. it is important to recognize predicting a more substituted and a less substituted enolate.
Because to get that one, the more substituted, would you just use the thermodynamic?
Mm-hmm. To get that more substituted, you could have used, and here's the cool part, you could have used hydroxide or methoxide or ethoxide or whatever you wanted. Ketones and aldehydes, they can react with any of our bases. Esters, we need to be careful about. I do want to point out one other thing. One of you, when taking the ester with LDA, wanted to go to the least substituted position. So you wanted to deprotonate from that least substituted carbon, because that's what LDA does. But esters only have one alpha hydrogen to go to, or one alpha position. Aldehydes only have one alpha position to go to. So with aldehydes and with esters, the thermodynamic and kinetic bases aren't really directing your regiochemistry. They're more so directing your equilibrium. It's ketones where thermodynamic and kinetic bases, sorry, I had those switched. No, I had that right. Thermodynamic and kinetic bases actually govern both your regiochemistry and your equilibrium. So ketones are kind of the odd man out. Aldehydes and esters are actually pretty easy. And I think it should be reasonable to say this can't happen because oxygen never loses its lone pair, which means all that's happening is oxygen is getting far too many electrons.
Can you ever use, you might have just said this, but just for me.
Yep.
So for esters, you can't ever use a kinetic base. Oh, well, we did. But for the top one,
You know what? Let's try to lay it out.
okay.
We'll start with aldehydes.
You're gonna use a kinetic base for the esters. The only one you can use is LDA. Right? But there's no other
You can't use terbutoxide with an ester because you would risk transesterification.
Right. That's why you're using LDA will be the only one that gives you the way you want.
Although to be fair, like LDA is better than terbutoxide most of the time anyways, if you want to control the equilibrium. If you want to get rid of all of that carbonyl and only have enolate present, you want to use LDA. Terbutoxide is going to still give you that equilibrium. So let's say that we have this aldehyde, and we react it with a small base like hydroxide and a large base like LDA. Oops, they give the same enolate. So why would you choose one over the other?
Cost, speed.
Cost, maybe. Speed, probably not.
Percent-wise, like how much you want.
Equilibrium. This might be, greater than 10% forms, but this will be greater than 99% forms. That's the only reason. Do you want to have both the enolate and the aldehyde in equilibrium, or do you want to have only enolate?
In the equilibrium you would want when we do the aldol equation.
The equilibrium you want when you have aldol and Claisen, unless you're doing cross aldol and Claisen. We're going to get into it more in the next unit. It's okay. This is our ester, RCO2R. I'm going to label this as just, I'll give us a specific one. I'll give us an OMe. And we'll react one of them with OMe minus, and we'll react the other one with LDA. Oops. Same products. So the kinetic and the thermodynamic don't have a choice here. There's only one place to form an enolate. So this, you're going to form greater than 1% of the enolate, and this you're going to form greater than 99% of the enolate. Now, if I were to expand this to show for the ketone, what I would actually do is give you 3 examples, not just these 2. Let's show what happens with something like a small base, ethoxide, a bulky base, tert butoxide, and a very good base, LDA. The small base is the only one that gives us the most substituted alkene, but both of our bulky bases give us the less substituted alkene. The alkoxides will give us something greater than 10% concentration at equilibrium, but only LDA will give us greater than 99% at equilibrium. So there is a usefulness to having both types of bases in each of these conditions. If you're trying to run Claisen reactions or aldol reactions, maybe you want your reactivity at the more substituted alpha carbon, maybe you want your reactivity at the less substituted, or maybe you don't want that reactivity yet. The unfortunate part with ketones is that if you want to do complete enolization, you lose the choice over your regiochemistry. You get one shot, that's it. All right, any questions on alpha carbon acidity? And the bases that we use. Okay. Then we're going to get into our reactions. Ready? Let's talk about alpha carbon halogenation. Or you could just call this alpha-halogenation. In acidic conditions, a couple of things to note. We'll deal with the more substituted alpha carbon, and we'll only be able to run one equivalence of this reaction. I'm going to say one equivalence, limited. I'm not saying that we're controlling the reagents here. We could have our reagents in excess. The reaction only runs once. How many of you took Gen Chem 2 here? Gen Chem 2 lab. Okay. We have an experiment in our Gen Chem 2 lab where we take acetone and we react it with iodine in the presence of HCl, and we make alpha iodoacetone. Now there's no regiochemistry in terms of more substituted, less substituted, but you can see the stoichiometry is limited to just one equivalence. There is a byproduct that forms in this reaction as well. That's HCl. And I do want to point out that we know the mechanism for this mostly already. In acidic conditions, the carbonyl is protonated. That's what happens in acidic conditions. Things get protonated. Then the conjugate base, chloride, tautomerizes the carbonyl into an enol. We've seen that mechanism. Acid catalyzed tautomerization. Was that just yesterday? Yeah, I think it was. But now we have an alkene. And do you guys know what alkenes do to elemental halogens? They react. Albeit this is not a normal alkene. This is an enol. So the oxygen plays a role here. Oxygen reforms the carbonyl and allows the alkene to attack iodine. That gives me back my protonated carbonyl form plus an alpha iodinated carbon. Now, iodide just acts as my conjugate base, deprotonates my carbonyl, and leaves me with my final product, plus an equivalence of HI. Now, what needs to happen next if this reaction were to run another time? First of all, the carbonyl would need to be protonated again, or maybe before deprotonation occurs. What would need to happen next is another enol would need to form. That means that this alpha hydrogen would need to be deprotonated. The issue is that now that this electronegative atom is on this group, and to be fair, iodine is not very electronegative, but it does have a lot of inductive effects still. Now that this group is on here, the entire system is a much, much weaker base. This becomes much, much more acidic because iodine is pulling electron density towards itself, and this becomes much, much less basic. So the iodine being present it inhibits this acid-catalyzed halogenation. It inhibits reactivity to the acid. That's a weird way of saying the iodine makes it a worse base. It's less likely to keep reacting. Now let's do an example where we see the regiochemistry in action.
I have a question here.
Yes, sir.
The products on the top of the HCl.
I sure did. And I didn't mean to. What did I mean to put?
HI.
HI. Thank you.
HCl will be just a catalyst, right?
That's right. This is acid catalyzed. Remember we said that with tautomerization yesterday. Acid catalyzed tautomerization. So this is all just acid catalyzed halogenation. So do you guys remember doing this in the lab in Gen Chem 2? It's your kinetics study. You ran a standard where you had one equivalence of acetone, one equivalence of iodine, one equivalence of HCl. and then you doubled the equivalence of HCl, you doubled the equivalence of I2, and you doubled the equivalence of acetone, and you figured out which made the reaction run faster. And the results of the experiment is that only HCl makes the reaction run faster, which is to say the rate determining step is conversion of the carbonyl into the enol. That's the rate limiting step.
But wouldn't there be also HCl? Or where's the HCl going? Just by
I did, actually the HCl reformed here.
Oh.
And because it didn't play another role, I just didn't show it again in the next steps. But you could show HCl going all the way down because it has no more role, but that doesn't mean it's not still there. Fair? Can you give me the major product of this reaction? Yes? No? You're off to a good start. Pen in hand. You've got the right placement, the right regiochemistry. Yeah. Good. Okay, so it's not hard for you guys to understand regiochemistry at this point. More acidic conditions, one equivalence of halogenation at the more substituted position. Great work. All right, condition 2, basic conditions. Once again, we're still going to go to the more substituted carbon. That's because we'll be dealing with our kinetic bases. This will substitute all equivalences of alpha hydrogens. And a caveat to that if you have a CH3 group attached to your carbonyl, it will actually remove that entire carbon from the carbonyl. That's a specific type of alpha-halogenation. That's called the haloform reaction. And I'll get into that in a second. Now, I'm going to be honest with you guys that most textbooks keep their reaction examples pretty generic, which means it's not always clear what happens in a condition like this, where you have 3 total alpha hydrogens, 1 on a more substituted side and 2 on a less substituted side. It is clear in all textbooks that this runs several equivalences, but it's not clear whether that happens on both alpha carbons or not. So you look in textbooks, you look online, you're going to see a lot of examples of this happening with aldehydes, where there's only 1 alpha position, or you're going to see this happening with ketones that have a quaternary carbon. So there's no hydrogens on that 1 position. You're only dealing with the other 1. And that's going to be what we look at as well. So you're not going to have to run into these confusing situations. So let's look at what happens with this aldehyde when we react this with Cl2 and NaOH in excess. Well, first, NaOH creates an enol, or enolate. The enolate then attacks the chlorine. From the alpha position, alpha halogenates itself. Having the chlorine there has made the compound a much better acid. Remember, having the iodine here made it a much worse base because it improves acidity, induction effect. So then a second enolate forms and a second halogenation forms. So the final product is 2,2-dichloro-3-methyl-butanal. Plus some interesting byproducts. NaCl twice and H2O twice. In our acidic conditions, the acid acted as a catalyst. But here, in basic conditions, the acid or the base is not acting catalytically. All right, I'm going to show both equivalences of the reagents that I'm going to need here. We're going to go through the mechanism pretty quickly. Hydroxide acts as a base, forms my enolate. Kicks off a molecule of water. I'm showing the enolate in its most stable form. But when it reacts, it's more likely to react from the alpha carbon. Because the alpha carbon is less electronegative, more willing to share those electrons. So the alpha carbon attacks the chlorine and gives me my first chlorine at the alpha position. So that kicks off a molecule of chloride, and then I've got another equivalence still of hydroxide and chloride. Oops. Forgot my chlorine. pKa changes here. pKa here, probably around 16. That's our secondary alpha carbon on aldehyde. pKa here, less than 16. Why? Because chlorine is pulling on the nearby electron density. So chlorine says, carbon, get rid of your hydrogen, take that pair of electrons for yourself. I will help stabilize that negative charge. Chlorine has an inductive effect that drops the pKa. This is not like when we looked at esters and said, esters are donating a lone pair into resonance. That type of induction increased the pKa, made it less acidic. This type of induction pulls electron density away from that group, dropping the pKa, making it more acidic. So this happens even faster than this because of that chlorine. Okay, now carbonyl reforms, alpha carbon attacks chlorine, kicks off chloride, and I'm down to my dihalogenated aldehyde. plus I get my second equivalence of chloride. Now I think you guys can see, I said earlier 2 equivalents of NaCl. You're okay with me leaving out the Na plus? Spectator ion of sodium hydroxide and sodium chloride. All right. A very specific case of these base run alpha halogenations is the haloform reaction. You guys are all very familiar with a specific type of haloform. Which one? Just run through all the versions of haloform that there could be. Fluoroform, bromoform, iodoform, chloroform. So this reaction is a synthesis of chloroform. You know what chloroform is? What it requires is something like this. Only alpha hydrogens on a CH3 next to the carbonyl. So this cannot go through the chloroform reaction. This cannot go through the chloroform reaction. This can go through the chloroform reaction, which is why it's really dangerous for you to mix bleach, Drano, and acetone all together. The Drano has sodium hydroxide, acetone is that carbonyl, and the bleach has the chlorine. If you mix all of those together over your toilet bowl, you're going to knock yourself out and maybe die, because you will produce chloroform from that reaction. And I say that not as like I'm telling you how to go make dangerous chemicals. That's like a warning, because I know someone is thinking, oh, now I know how to make chloroform. Yeah, now you know how to kill yourself over your toilet bowl. So let's take acetone. Let's take Cl2. You know what? Actually, let's not take acetone. I'm going to make this acetophenone. So benzene on the other side. And we'll take sodium hydroxide. This is going to be in excess. I will need 4 equivalences of hydroxide, 3 equivalences of chlorine. The product that we get here is carboxylate, and specifically benzoate and chloroform. You swap this for Br2, I2, you get bromoform or iodoform. Now, we don't have the time to go through that whole mechanism, but it's not really worth it to go through that whole mechanism anyways, because we just looked at most of it right here. So let's jump forward to the part where all 3 of the alpha hydrogens have been substituted for a halogen. Now I have a trichloroketone and a trichloroalpha ketone. What happens here is surprising. Hydroxide acts as a nucleophile. Gives us this tetrahedral intermediate. How often do carbon-carbon bonds break? Rarely. It's incredibly hard to break carbon-carbon bonds. And that's because carbon is not a good leaving group. Carbon doesn't like to take electrons for itself. But think about a carbon that has 3 chlorines pulling on its bonding pairs. That carbon can actually hold a lone pair fairly well, because it's not just carbon holding that lone pair, it's 3 halogens pulling on that lone pair. even still, this is acidic, especially in the present, or excuse me, this is basic, especially in the presence of an acid, like a carboxylic acid, which has just formed by this reaction with hydroxide. So the last step here is a deprotonation that yields us chloroform and this carboxylate. You just run an acid workup, you've got a carboxylic acid. Okay, I apologize. I've taken us past time. When we come back in on Tuesday, because we don't have any lecture tomorrow, when we come back in on Tuesday, we're going to look at a similar reaction, basic conditions, that allows us to alkylate our alpha positions, not halogenate. Then we're going to turn in to look at the aldol addition, aldol condensation reactions, Claisen condensation, Michael addition, all sorts of good stuff.
That's the last week.
Yeah, that's our last week of class. A lot of really fun reactions. So make sure that you skim and scan and maybe even go through the homework to see what types of questions are you going to be confronted with when we go through this material. Because we'll be doing a lot next week. All right? Okay. Have a good weekend, guys.